Okay, let's talk through these notes on titration analysis now. Now that I've shown you what a titration looks like, let me just walk you through again, just on paper, some of the key terms and concepts that we're using here. Okay. What's going to happen in a titration is you're going to have something unknown about a sample. In the lab I just showed you, or the demo I just showed you there, we had an acid that we did not know its concentration. And so our goal, the whole point of the lab, is to try to find an unknown sample concentration. That's usually our goal. Usually it's about trying to find a moles per liter of something. You can actually do titration to try to find grams or something else as well, but that's usually where we're going to start. Okay. The key is that you have to have a measured volume of the unknown concentration. This unknown sample here, we're going to know its volume. Usually it's going to be 0.0100 liters because we use a pipette. Now it doesn't have to be 10 milliliters. We can use 5 or 25, depends on the size of our pipette. But we should always know how much volume of the sample there is because we actually measure it. Okay. The titrant itself, we also should know its volume because we can find the two values and subtract them. The problem is, though, the titrant has to be a known concentration. And for it to be a known concentration, I'm going to say this a lot over the next few years as we do this, you need to make it yourself. If you don't start from scratch with a solid, a primary standard solid, make the solution yourself, you can't trust the authenticity. Even if I make you a solution and I say, trust me, the concentration is 0.5 moles per liter, you can't trust that because you didn't do it yourself. Does that make sense? There's actually one more reason why as well. Solutions, usually the concentration of solutions is very difficult to maintain. Anybody have any ideas why it's difficult to maintain a concentration of a solution? What are solutions made from? Sure. What is probably almost always one of the chemicals, the solvent? What's almost always one of our solvents? What happens to water slowly over time? Yeah. Which means that if water has the ability to evaporate, granted it's slowly, right? That means that the volume of solvent is changing. It means your concentration changes. So even if I tell you that it's 0.5 moles per liter, it can actually change its concentration overnight just due to slight evaporation properties of water. Does that make sense? So. Basically the concept is we want to use an indicator, and the indicator we use is phenolphthalein. You can do other indicators if you want, but phenolphthalein is excellent because it has a very distinct endpoint. That's a word I want to start using more and more. The endpoint is the spot where you can visually see it go from clear, transparent color to pink. Now we want just the faintest of pinks. The idea being with the faintest of pinks that hopefully the amount of acid and base is basically exactly the same, exactly to about the nearest drop that we can have. Technically there's going to be slightly more base than acid because the base is what causes it to stay a pink color. Does that concept hopefully make sense, that the acid and base are neutralizing each other? That's why it doesn't remain pink. But when it does remain pink, the acid and base can't neutralize each other anymore because the acid is limiting and therefore missing and gone. And so that's why it remains pink. If you guys were to look at my trial, mine probably looks more like this one where it's quite a bright pink, too far. You guys know how I put in 2 drops? I think I actually put in 1 drop too many. It probably should have been the first drop. And that means my results are slightly inaccurate. I mean, only by a drop, but still, a drop is enough. When I was in university, my labs were based on whether or not, like my professor would tell me, find the concentration of the solution. And let's say the actual concentration was 0.2 moles per liter. Well, if I said it was 0.25 moles per liter, that's what my grade was based off of, as to like how close I was to the true answer. So, although like in a high school lab like this, I'm not going to actually grade you based on whether or not you're correct or not. I do want to help give you guys those skills that you might need if you go on to take a university level lab. I actually had a really cool moment about a month ago. You guys know Raj. He was actually asking my advice on how to set up a lab for his UBC chemistry course where they were doing titrations. And it was kind of cool for me to talk to him about that because we had done so many that he didn't really need my help. I think he just wanted reassurance. But like he knew what he was doing, and I feel like in part it was because we had done titrations in high school so many times that when he had to do his own lab, he knew what to do actually. It's kind of cool. So, but I almost want to guarantee his grade though would be based on how well he did his titrations. So, anyways, what else can I talk about here? Just another picture here of the idea. An endpoint should be just the faintest of pink. If it's too dark of a color pink, it means you probably went too far. Sometimes the word we'd use, it's like an overshoot. Okay. One more thing. If you were, say, Raj at UBC trying to determine a concentration and your mark depends on it, are you going to do it once? No. Right? Like good scientists, in order for something to be conclusively proven, they don't just do something once, they do it multiple times. As a general rule of thumb for this class, you're looking for 3 results within 0.2 milliliters. Or another way of phrasing it, 0.2 milliliters means plus or minus 0.1 milliliters. Like you could go up by 0.1 or you could go down by 0.1. You're looking for 3 results in that range. Let me give you some examples. Let's say the first time I do it, I get 4.0 milliliters. That's how much volume it requires. Remember how like from here to here was 4 milliliters? I did that the first time. But I mean, I should just do it once, so I do it a second time. And the second time I get 4.2 milliliters. Is that within a range that's reasonable? I'd say yes. Let's say the next time I get 4.2 milliliters. That's still good. Let's say that I got 4.7 milliliters. That one's like too far away. Does that make sense? What we're going to look to do is find 3 results and then average them. However you spell average. Average. So like just add them up and then divide by 3. Does that make sense? Often what will happen when you do a titration is you'll do trial 1, it'll be 4 milliliters. And you do trial 2 and it'll be 4.7 milliliters. And you'll be like, this sucks. Because like you're clearly not within 0.2. Okay, I just want to add some context though. 0.7 of a milliliter, like a milliliter, in terms of reference on the scale, from here to here, if you guys can see where my thumbs are, that's a milliliter. 0.1 of a milliliter is like that far apart. Like a point something of a milliliter is sometimes literally like a drop. Right? So that's why you need to be precise and accurate to basically within a drop of each other. So maybe this one's too far. Then you try another one and you get 4.5 milliliters. Well, the 4.5 goes much better with the 4.7. Does that make sense? Because they're fairly close. And let's say the next time that you did this, you got 4.6 milliliters. Now you might start saying, hey, look, I've got some volumes that are fairly consistent. Does that make sense? Consistency should hopefully correlate with accuracy. Now, when I did my labs in university, and I can't speak to Raj, but like when I did mine, I wouldn't even just do 3 trials. Right? Like if they gave me 3 hours to do the lab, I would use all 3 hours. Why not, right? Like why leave early if my mark depends on it? And so if I had 3 trials that were close, I would do it again and again and again. And in theory, if I could make the next trial be 4.5, and then the next one could be 4.6, and the next one could be 4.4. And then maybe I have a trial that it happens to be 4.1, and I go, well, that's probably an error. Does that make sense? Hopefully, if I have a whole bunch of trials that are all within that same range of 4.7, 4.5, 4.6, the consistency means that I'm doing it correctly. Does that make sense? Okay. From there, it just is a case of doing some math then. It almost always works out the same way, the way the math works. So you may want to just write this somewhere here. Math for a titration. First thing you need to have, if you don't have it already, is you're going to want to take a grams number. You're going to want to use a moles per grams number. And you're going to want to go 1 over liters. This is always your first step. How are you going to find a grams number? What sort of apparatus do we use? Good, a scale, yeah. You're going to need to weigh something on a scale. In our example, I had just a few flakes of sodium hydroxide. I had weighed it on the scale before you got here. I had said it was 0.331 grams. Then you want to moles over grams. Where's this number coming from? Yeah, it's the molar mass. Now, in the example I did, it was 40, but I don't want to write in that it's 40 because what if we didn't use sodium hydroxide? And you got to change the molar mass. And then one last thing, you need a number to go down here for liters. Well, this is the size of your volumetric flask. This is the size of the flask that you made your solution in. Most of the time, it's 100 milliliters because that's the only size of flask I have. But in theory, it could be a different number if you're in a different lab. If you do this work right here, what does this find you? It finds you a concentration. And I'd like to call it a known concentration. Why? Why do we know it's concentration? Because we made it ourselves. Yep, that's step one. Then for step two. Then you actually do your titration. And in doing your titration, you're going to get a whole bunch of different values. The first one is going to be a liters value. Chances are this liters value is going to be the average. No, I take that back. What do we do for our first liters value? We used the... No, that's right. This will be your average volume used. So you know how like I was averaging 4.4, 4.5, 4.6? This should be your average volume that you use. Well, we don't want liters, so we're going to multiply by moles per liter. That'll cancel out liters. Where am I going to find that moles per liter number then? We just calculated it. Does that make sense? This moles per liter that we just calculated, that's what comes there. Because we have to know at least one concentration because we make it ourselves. Anyone remember what comes next? Stoichiometry problem. Yeah, you need a ratio. Okay. Now, I kind of skipped that in our example because I didn't tell you what the acids and bases were, but at some point you need a ratio, which means you need a balanced equation. Last step. Most of the times I'm going to ask you to find a concentration. So I'm going to ask you to find a concentration. Currently your unit is in moles. We need it to be moles per liter. So I find the best way of showing that is just go 1 divided by a liters number. We just need to know what that liters number here is. Well, this is the liters of how much sample you used. How did we measure the sample in our lab there? What tool did we use? The pipette. Yeah. So this would be the size of the pipette. If you do all of this work, it should give you a moles per liter value of your unknown. This is kind of the basic setup of any sort of titration. Does that make sense? Even if it doesn't, I find this frustrating to teach. You have to just do titrations. Like that's why I'm a big believer that chemistry has to be like a done sort of act. You can't just talk about it on paper. So that's why Wednesday, Thursday, Friday, I'm going to have you guys do a titration. I actually have you guys do multiple titrations over the course of the time I teach you, because I really do hope that if you end up going to university and take chemistry courses, that like you are experienced. When they hand you materials, you'll be like, I know how to use a pipette. I know how to use a burette. Right? But I mean, you'll probably know people that are being classes there will be like, I've never touched lab equipment before. I want to make sure that if you take that route, that you're comfortable doing this. Believe it or not, I didn't realize this until I talked to Raj. One of the lab you guys are going to do, kind of along with one of the grade 12 labs, was actually a university lab. It was like exact repeat of something we did in high school. And I know I do other labs with my grade 12s where I did them in university. So I will try to do university level labs so you guys have that experience. Okay, here's a little movie just kind of describing the steps you have in a titration. So first step, you got to fill your burette with titrant, and you got to make sure that you empty the tip. And you always have to take the initial reading. You have to know how much initial volume there is. Then you have to add some to the flask. Now, they actually added it using the burette itself. I prefer using a pipette. But they actually are using two different burettes here. Don't forget to add your phenolphthalein. Remember how I screwed up adding in phenolphthalein? Make sure you add it. So then they're using a second pipette for the other one. Again, you need your initial reading. Then you're going to start adding some of the titrant. As you add the titrant, it should turn pink. But as you swirl, it should disappear. Eventually, as you add the titrant, the color will remain. It won't disappear quite as well because you're running out of your limiting reactant, which is the acid in the bottom. And hopefully at some point it will stay pink like it's doing right here. As soon as you find the exact drop you're hoping for that it stays pink, find your remaining volume. And hopefully it will almost kind of fade away and become very light pink. If you guys look at my flask right here, I think I overshot it by a drop. As you can see here, here's one that's faint pink, and here's, oh, it's gone there, faint pink and dark pink. You're hoping for a very faint pink. That would be the most accurate you could be. So, okay, let's try some calculations then. Let's just practice the math behind this. So, I like to recommend, at least when you start, draw a picture, just so you have an idea of what goes where. So it says that you've got a 50 ml sample of an unknown concentration of HNO3. So as I kind of draw a picture here, here's a burette. Here's a flask for it to go in. And what it's telling me is right down here, this is 50 milliliters of an unknown. At least I know there's 50 milliliters there, though. I actually get to know what it is, though. At least I get to know that it's HNO3. I just don't know its, I don't know its moles per liter, though. In the burette, we're going to use 65 mils of titrant. So that would be like from here to here when it eventually drops. That's 65 milliliters, and that is of sodium hydroxide. Okay, I have to cheat a little bit on this one. There's a concentration there of 0.400 moles per liter. In a lab setting, you couldn't trust that number because you didn't make it yourself from scratch. Does that make sense? But in the context of this question, we're going to have to assume that you have already made it from scratch, and we have to assume that number is trustworthy. But does that make sense, the difference between the two? Like in a lab setting, if I give you a flask and say, here, trust me, this is 0.400 moles per liter, you would never do that. It's just, you can't trust its authenticity. But here, I guess we can. So you know how that whole step one part where you have to do grams, divide by molar mass, divide by size of container? We actually get to skip that on this step here. We can go right to step two. So it usually looks like this. A liters times by moles per liter times by a ratio times by 1 divided by liters. Titrations almost always have the exact same setup. Any idea where I should start? Well, I need a liters. Well, I have 50 milliliters and I have 65. So I have to pick one. There's only one right one to start with. Any ideas which one? It is the 65. Can you explain why? We know its concentration. Because you know how right afterwards we're going to need to have a moles per liter number? Since we know this guy's concentration, we can put those together in tandem. I can put the 0.065 liters right next to the 0.400 moles per liter. Like those two numbers have to work together. By default, then, the last number, the 1 over liters, that 50 milliliters, that was measured probably using some sort of pipette of some type. The 50 milliliters will have to go here. 0.050 liters goes there. Does that make sense so far? We're really waiting on one thing then. We need to get our ratio. In order to get a ratio, we need to write a balanced equation. So the balanced equation is going to be HNO3 adds to NaOH. Basically acid plus base. So what happens when you add an acid to a base? What does it make? Water and salt, yeah. So H2O is one of them. The salt will be NaNO3. I'm just going to write aqueous for all states of matter here. I guess liquid for water is actually probably smarter. Balancing it. Actually, it's balanced. It's perfect. So the only thing I would suggest then is we should just make sure we know which one is which. This information here was about NaOH. So I'm going to put NaOH on the bottom so that it cancels. And it's a 1-to-1 ratio with HNO3. So it means by the time I'm done, the things that didn't cancel, there's a moles left, there's a liters left. It's of HNO3. I just need to do the math and calculate what it's going to be. I got 0.52 when I'm done. Anybody else calculate that? Okay. Do you remember the terms qualitative versus quantitative? We've been talking mostly about quantities in this section because it's all about numbers. But we did have one day where we talked about qualitative analysis. That's where we talked about things like flame tests and colors, and you had to do things like separate based on filtration or gas collection. Do you guys remember that lesson? That lesson really focused on the what is it. Now the good news is we don't actually have an issue in a titration of not knowing what something is. We know exactly what it is. We know that it's say sodium carbonate or acetic acid or something like that. That's not the problem. But sometimes the issue is we don't know how much of it we have. How do you measure a mass of something? Well, you just weigh it on a scale. How do you measure a volume of something? Well, you use some sort of measuring device like a pipette, a volumetric flask. But here's the hardest question. What if you want to know something's concentration? There's no device where you just put a beaker of something on there, find its concentration, it just tells you a number. Does that make sense? So if you ever want to find a mass, use a scale. You want to find a volume, use a flask of some kind. But if you want to find a concentration, it's quite complicated. You have to do all of this titration stuff. That make sense? All right, why don't we skip ahead then? Well, actually, I guess I really only have... Why don't I do one more example, and then I'll call it a day. And then I have 3 examples after that, but I'll have you guys try those just as your own practice. I should just point out here, this slide here, before I do that last example, I've already used this word here, the term standardizing. Standardizing means that you need to know its concentration because you make it yourself. Here's the definition for primary standard. Primary standard is a chemical that's pure. Do you guys know what anhydrous means? Okay, there are certain chemicals that when we make them in a lab, we have to make them by doing, like, say, crystallization. Remember crystallization, where you like take a solution and you just basically evaporate off the liquid and the solid remains behind? The problem is that sometimes, although most of the water evaporates, sometimes some water molecules kind of stick behind in the solid. And maybe I've shown you one of these before, maybe not. Like barium hydroxide with like an 8H2O afterwards. Have I ever shown you a chemical like this where there's like a dot afterwards? Maybe lab has done this before. This is a hydrated molecule where essentially what you have is barium hydroxide. But the barium hydroxide has like 8 water molecules that kind of tagged along. And those are water molecules that didn't evaporate during the decrystallization process. They just kind of found a way to like sneak into the solid and just attach themselves in there. Does that make sense? We don't want to use hydrated substances then, because that's not useful. So you can't use liquids or gases, because once you open it, the amount cannot be guaranteed. Liquids evaporate. Gases escape. But solid stuff I can be very confident that when I measure it on a scale, it will remain the same. Yeah, you guys can read this. Let's do our last example, then I'll call it a day. I've been talking a lot today. Last one. You have a sample of unknown H2SO4. So again, I always recommend just draw out a picture just to get started. You need to have a burette. You need some sort of flask. And it says that your unknown Again, it's not unknown in terms of what it is. We know that it's H2SO4. What we just don't know is its moles per liter. We don't know its concentration. But we do know how much there is because there's 75 milliliters. How could I know that there's 75 milliliters? We just need some sort of measuring tool, right? We could use pipettes. We could use volumetric flasks. We could, in theory, use the burette itself. But it's easy to measure a volume. Volumes are easy to measure. We also know that in the flask itself, we used 57 milliliters of titrant. And the titrant looks like it's calcium hydroxide. Again, normally the calcium hydroxide has to be prepared yourself using a primary standard. But we'll take its word for it that it's 250 moles per liter. We'll just, in the question like this, just assume that you actually did make it yourself. That's all we need. Titration starts with a volume, then a moles per liter, then a ratio, and then 1 over a volume. You just got to get the numbers in the right spot. Where should we start? Actually, that's not a bad idea. Let's do a balanced equation. We don't need it yet, but may as well do that. CaOH2 plus H2SO4. You need water, and you'll need a salt. You guys okay with being able to write an equation like this? Like a double replacement reaction where the H's and the OH make water and the calcium sulfate goes together? What do I need to do to balance it? That'll do it, actually. Yeah, 2 in front of water will pull this off. That's all you need. The 2 examples I've done that are very boring. In terms of your ratio is 1 to 1. But let me tell you, it's not always 1 to 1. It could be 2 or 3 to 1 or something like that. 3 to 2. Where do I start down here? Which liters number do I use? 57 or 75? 57 is correct. Why? You have to start with a known concentration. So the 57, the 0.057, will go with the 250. And that's for the calcium hydroxide. Make sure that the 2 numbers that go together, like these 2 numbers here, they go together. That's where you're starting. You have to start with something known. Then we don't want to know about calcium hydroxide anymore. What we'd rather know about is H2SO4. But again, it's a nice 1 to 1 ratio, so that doesn't change much. And then last step, we want to divide by the volume of H2SO4, so that's 0.075. I'm just dividing all those by 1,000, by the way. So that's it. Just need to... I got 0.19 when I'm done. So just in terms of, I'm a huge fan, you guys have heard me say this before, of unit canceling. This liters cancels, that calcium hydroxide cancels. That's actually it for canceling. So what you're left with is a moles unit on top, a liters unit on the bottom, and H2SO4 indicates the type of solution. So we now know the concentration of the acid. So one more time here. You want to measure a solid? Use a scale. You want to measure a liquid? Use literally everything I have in those containers. They all measure liquids. But if you want to measure a concentration, concentration is very difficult to measure. The most accurate way of doing it is a titration, which sucks because there's a lot of steps to it. First, you have to make yourself a primary standard solution yourself using some sort of weight on a scale, make a solution, and then use that as your known concentration, titrate it until the endpoint turns pink. At that point, that's when you know when to stop. And then you can do a math calculation, and that will find you a concentration. So quantitative analysis for concentration actually kind of sucks. Does that make sense? Yeah. Okay. If you guys want, maybe I'll just leave this up to you. You could try these additional practice questions if you want more practice. If you feel like you've got the hang of it, that's fine too. So, why don't I end that there? Tomorrow we're going to do one more set of notes. It's actually a fairly short section. It's just talking about how we can graph the pH of different things as we titrate. Like I said, then Wednesday, Thursday, Friday, I'm gonna have you guys do a titration because I really want you to have hands-on practice with this. And then next week, Tuesday and Thursday, or whenever, actually, I don't care. You have a couple quizzes. Does that make sense? So, yeah, spend the rest of today working on whatever it is you need to work on most. I don't know, whatever's most important, I guess. So, one other thought for math, you do have a math quiz next week as well, and one this week. I don't remember what day the one this week is, but I want to think maybe Thursday this week, and then next week we also have one. So you may want to kind of stagger your tests on alternate days. But anyways, that's it. That's all I got. Let me know how I can help otherwise.